Hello, and welcome to my talk about additive pattern databases for decoupled search. My name is Silvan Sievers and I present joint work with Gnad and Alvaro Torralba. Let's start with the motivation for our work. As you might know, a state-of-the-art approach for optimal classical planning is explicit heuristic search with abstraction heuristics. Also, recently, a lot of work has been done in decoupled search. However, so far, there is no direct and practical way of using abstraction heuristics in decoupled search. In this work, we want to change this, and we contribute an investigation of how to use pattern databases and how to additively combine them in decoupled search. We will be considering planning tasks in finite domain representation in this work, which means that states are represented as assignments of state variables to their values. Furthermore, we will be using pattern database heuristics. So let's briefly recap what they are. Pattern database heuristics are based on projections of the set of state variables of the planning task to a subset, the so-called pattern. This projection induces an abstraction, and we can fully solve the abstract task and then store all of the resulting perfect heuristic values in a database. This database can then be used during search as a lookup. We also need to talk about decoupled search briefly. In the preprocessing step, decoupled search computes a factoring of the state variables. That is, it partitions the state variables of the planning task into a center factor and one or more leaf factors. This decomposition of the planning task cannot be arbitrarily, but it has to be such that the only dependencies between factors are such that leaf factors may depend on the center factor, but there is no dependency between variables involved in different leaf factors. Why can this be useful? Well, because it allows to restrict branching of the search over center variables only and actions related to these center variables. And we can handle all of the leaves separately. So a decoupled state during decoupled search consists of two components. First, the center state, which is an assignment to the center variables only, and then a pricing function, which maps all of the leaf states to the cost of reaching them in the current decoupled state, which means that we need to compute all of the leaf states which are reachable, given that we are in the center state. Therefore, a decoupled state represents exponentially many explicit states, which are also called member states in that context. Now the question is, how can we use heuristics for decoupled search? And all previous approaches are based on the so-called by-leaves compilation. Since we somehow need to make the information about the leaf prices available to the heuristic and cannot directly use explicit heuristics because they don't know about these prices, the idea is to compile the price information depending on the current decoupled state into a compiled task, and then to use the explicit heuristic on that compiled task. This application has two problems in our setting. So first, the general problem is that this can be information lossy. For example, if we use the delete relaxation, we would ignore certain aspects of the newly introduced variables and actions. But also, and more importantly, since we plan to use abstraction-based heuristics, which are usually entirely pre-computed before search even starts, this is impractical here, because for every state evaluation, we would need to recompute the whole abstraction heuristic because we have a new compiled task. Therefore, we were looking for alternative ways of using explicit heuristics in decoupled search, and came up with this direct definition, so to say, which we call the explicit decoupled heuristic. Why explicit? Well, because we explicitly enumerate all the member states of the decoupled state and then minimize over them and minimize the sum of the price of the explicit member state and its heuristic value. This turns out to be the best that we can do. We compare this to the by-leaves compilation, and it's actually better, it can be better. However, the problem clearly lies in the fact that we need to compute the exponentially many member states. So then we decided to look at pattern databases and to see if for pattern databases we can do any better than that. And we started with single PDB heuristics. So if we look at this definition of the explicit decoupled heuristic, we might think, well, do we really need to consider all of these explicit member states since we're only talking about abstractions and we are abstracting anyway? The answer is no. We can actually replace that by only considering abstract member states. So by doing that, we don't need to enumerate all of the explicit member states, but it suffices to consider the abstract states. This means that we can efficiently compute a single PDB heuristic for decoupled search. However, it is only a single PDB, and as you probably know, single PDBs don't scale very well. What people instead normally do is they combine multiple PDB heuristics, and here we assume that we consider the canonical combination. That is, we are given a set of additive sets of PDB heuristics, and we maximize over these sets, and within each set, since we know that the heuristics within the set are additive, we take their sum, and this is an admissible combination of heuristics. Now the question is, how can we transfer this to decoupled search? In our first attempt, we tried the naive way, which we call the naive combination. So by looking at the canonical heuristic, we thought, well, we just figured out how we can compute a single PDB heuristic. Can we not simply plug this in where we compute a heuristic here? And of course we can do so. So that means that we still maximize over all additive sets, and for each additive set we still compute a sum, however over the decoupled PDBs now. That means we compute decoupled PDBs individually and sum up their heuristic values whenever possible. Now there's two problems with that. First, this can be information lossy because since we compute PDBs individually, we are free to choose a different minimizing member state in the computation of the heuristic value in each PDB, which is not what we could normally do. Even more problematically, this is actually also an inadmissible combination because we can count the prices of different leaf state multiple times in different PDB heuristics. That means the naive combination does not work. Instead, we went back to the explicit decoupled heuristic that we defined and that you see over here again, and thought, okay, let's give that one again a try also for the canonical heuristic. And what we can do is we simply replace the single heuristic h of s here by the canonical heuristic, and we obtain the explicit decoupled canonical heuristic. And of course, this has again the drawback that we need to enumerate the exponentially many member states. And indeed, in the paper, we formally show that this is an NP-complete problem. However, we thought that it would still be interesting to implement this, also to see how good the explicit decoupled canonical heuristic can be. And what we did is we used a branch and bound algorithm that recursively and thereby incrementally enumerates the member states and allows for pruning, because whenever we find that the partial sum of prices and heuristic values for a given member state already exceeds the current minimum, we can skip all of the recursive calls from that branch. Of course, in the worst case, this still has exponential runtime, which is why we also finally looked at polynomial time approximations. Now let's look again at this explicit decoupled canonical heuristic. And we by now figured out that the problem is the enumeration in the minimum. So we need to find the minimizing member state S, and only then can actually compute a heuristic. And now if we assume that for some reason we know that we can do this independently for each additive subset, well, we can move the maximum operator out of the canonical heuristic in front of the minimum of the explicit decoupled heuristic. This is a admissible way of doing things, but it is still lossy because now we lose the interaction of different additive subsets. However, we were able to figure out two scenarios by restricting the way PDBs interact with the leaves, in which scenario this way of combining things actually becomes exact again. The first one is leaf disjoint PDBs, where we require that each additive set of PDBs only consists of pairwise leaf disjoint PDBs, which means that no two PDB heuristics in that additive set affect the same leaf. And the alternative, the second approximation, is that each PDB, wherever it is, only affects at most one leaf. Both of these approximations result in a similar situation, namely one where we can consider each leaf factor independently of the other leaf factors, and this is exactly what we want to do in decoupled search, because we know that there is no PDB or no PDB involved in an additive set that needs to consider several factors at the same time. And this really allows to compute these additive sets independently of each other, which justifies moving the maximum in front as we did. And we formally show that the heuristic value indeed equals the explicit decoupled canonical heuristic, so it is the best that we can do. Finally, we ran some experiments on the IPC benchmarks with two factoring strategies, namely fork factorings and maximize leaf mobility factoring. And the first experiment we did is to run explicit state search with normal PDBs and then with the two ways of restricting PDBs. So leaf disjoint, computing leaf disjoint PDBs only and single leaf PDBs only, because we thought that these restrictions might affect heuristic quality quite significantly in a negative way. And it turns out that this is indeed the case for the leaf disjoint pattern databases, but not so much or not at all for the single leaf PDBs, which was quite surprising. Then we proceeded to evaluate decoupled search, and we started by evaluating the explicit decoupled canonical heuristics, so the exact computation, which is possibly very expensive. And there we first did it in the stupid, non-optimized way, and we found that coverage results cannot really compete with explicit search. However, results got a bit better when we used our branch and bound algorithm with pruning and early stopping. However, still not really competitive with explicit search. Then we proceeded with the two polynomial time approximations, and as we expected after seeing the bad impact of the leaf disjoint restriction, coverage cannot really compete even with the explicit way of computing the heuristic. So this is not an approximation that we can recommend. However, the single leaf approximation works really well, and in particular with the fork factoring, it actually works better than explicit search. So it's time to wrap up. In this work, we investigated an alternative way of computing explicit heuristics for decoupled search in general, then turned our attention towards PDBs and showed that we can efficiently compute single PDB heuristics for decoupled search, and that this is not easily possible if we want to admissibly combine additive PDBs. However, we still found a practical implementation and presented two polynomial time approximations for that problem. Thank you for your attention.